So this brings us to a place in the chapter where we're going to talk about reaction mechanisms, or how reactions actually take place, what the steps are for a particular reaction. So the fact of the matter is, most chemical reactions don't occur in one step. They occur by a series of steps, and we call that series of steps the reaction mechanism. Now, there are reaction mechanisms that are single-step reactions, and we will address those. But for now, we're going to presume that reaction mechanisms, that is, reactions occur by more than one step. So 2, possibly 3, and we'll keep it simple. Most of the time, we'll just work with a 2-step reaction. So reactions that we have discussed to date simply tell us what reactants are used and what the products are formed, and the stoichiometry, that is the ratio of this reactant to that product, just the coefficients, okay? So let's say 2A react with 3Bs to form 4Cs for our product. Things like that. That's what you know so far. They don't give you the information on the reaction mechanism. That is, what are the actual steps? I mean, does A have to react with another reactant A before it reacts with another reactant B? And what are the steps in that particular process? So chemical kinetics, this study of reaction rates, gives us a tool that we can use to determine what a reaction is, a reaction mechanism is. Now, I want to stress this. You can never prove a mechanism. What you can do is establish a series of criteria that are consistent with an experimentally determined rate law that gives you information on what the reaction mechanism probably is, okay? But you can never actually prove a reaction mechanism, because you can't actually get down there on the atomic molecular level and watch which molecule is reacting with another molecule and exactly what the steps are. But you can get a very good indication of what a mechanism is, and chemical kinetics gives us a tool for doing that. So every reaction that we've studied so far, you have some kind of stoichiometry. So here is an overall reaction. We've got nitrogen dioxide. It combines with carbon monoxide to produce the products nitrogen monoxide and carbon dioxide, and the coefficients happen to be 1 for all the components in this reaction. Now, this could be a single-step reaction, but if we go into the lab and we perform a kinetics experiment to try and determine the rate law, and we determine that it has this rate law, well, there's some peculiarities about this rate law that tell us that this is not a single-step reaction, that there's something else going on. In the first case, we have nitrogen dioxide, which is one of the reactants, and that's in the rate law, but carbon monoxide is also a reactant. It's also necessary to produce these two products as a result, and yet there's no carbon monoxide in this reaction. So effectively, carbon monoxide is 0 order in this reaction. And if it's 0 order in the reaction, that means that the carbon monoxide has to be present for the reaction to take place. It is, after all, one of the reactants in the reaction, but changing the concentration of the carbon monoxide does not affect the rate, because, as you recall, anything to the 0 power is equal to 1. So really, this is the rate law for the reaction, and it happens to be second order in nitrogen dioxide. So we have to think about it. So we're going to propose a mechanism. And the first thing we're going to propose in the mechanism is an initial step. Now, each one of these initial steps, we call those elementary steps. So this is step 1, and it is an elementary step. It's not the whole shooting match. It's just an elementary step in a proposed mechanism. And what we're going to say is that in order for this reaction to take place, and this is based on principally that nitrogen dioxide is second order in the experimentally determined rate law. We did an experiment. We determined that this was the rate law, that carbon monoxide was zero order in this reaction. All right, so we're going to propose this as an initial step, and that one nitrogen dioxide molecule has to collide with another nitrogen dioxide molecule. Now, there's no carbon monoxide here, so we can't have any carbon products over here on the product side. And what we're going to propose is that we have an exchange of oxygen between the two nitrogens, so that we add one oxygen to one of the nitrogen dioxide, and that's going to produce this product, nitrogen trioxide. And here's the other nitrogen oxide component, and that nitrogen oxide component, that actually is one of the products of our reaction. However, there's no nitrogen trioxide as a product in this reaction. So we're going to suggest that this is an intermediate in this reaction mechanism. Now, keep in mind, we are hypothesizing here. In a sense, we're making a guess about this proposed mechanism. All right, so if there's no nitrogen trioxide in the overall reaction, it doesn't appear and we can't see it, then it must be an intermediate, and intermediates are going to be consumed in subsequent steps. So here is that intermediate, nitrogen trioxide, and it's a reactant in our second elementary step. So this is again another elementary step, and this intermediate is now a reactant, and it's going to get consumed. It's going to collide with carbon monoxide, which has to be in here somewhere because it is a reactant in this reaction. It's zero order. Changing the concentration doesn't change the rate, but it has to be in the reaction. And when it combines with the carbon monoxide, has its collision, it reforms nitrogen dioxide. It's actually taking an oxygen from the nitrogen trioxide, reforming nitrogen dioxide and forming carbon dioxide, which is one of the products of the overall reaction. So here's what's going to happen in this proposed mechanism. We can actually cancel out the nitrogen trioxide intermediate. You'll recognize intermediates because they form in an earlier step and they're consumed in a subsequent step. And then, since we've got nitrogen dioxide as a product of the second elementary step and as a reactant in the first elementary step, we can also cancel the nitrogen dioxide. Okay, so I think I'll stop on this slide at this point and just reiterate a couple of things. So the way we get at a proposed mechanism, which is really kind of a guess, it's an hypothesis, is we do a kinetics experiment. We determine the rate law for an overall reaction. Once we get that rate law is going to be a clue to figuring out what the proposed mechanisms is. And we have to think about it. We have to do some critical analysis on what that mechanism may actually be. Remember, each step in a mechanism is an elementary step. So let's talk about molecularity. And the first thing we want to say before we define molecularity is it's the rate of an elementary step is determined by its molecularity. Well, what do we mean by that? Well, the molecularity is simply the number of species that have to collide to produce the reaction indicated by that step. So is one molecule required, or 2 molecules required on the reactant side, 3 molecules, etc. So here is a unimolecular reaction, and we can simply say that in a unimolecular reaction, we could have, let's say, just symbolically, I've got this, and this reacts to form some product B, maybe product C, but there's only one molecule here. And because there's only one molecule here, it's unimolecular, all right? And then we can have bimolecular reactions in a couple of different types. I could have, let's say, A reacting with another A to produce, I don't know, something like this or this. This is bimolecular because here's one molecule, here's one molecule. They have to collide in order for that reaction to take place, so we would call this bimolecular, okay? And then if we have a Ter-Molecular reaction, that would be 3 molecules have to collide. So we'd have something like A plus B plus, I could have another B here. This is still Ter-Molecular because even though I've got the same molecule here, this molecule and this molecule are 2 discrete molecules that have to collide with another molecule to produce some kind of product over here. So this would be a Ter-Molecular when 3 molecules have to combine at the same time. And this is actually a very rare occurrence. Bimolecular, pretty common. And by the way, A plus B going to products, this is also going to be bimolecular. Okay, because here's a discrete molecule, here's a discrete molecule, these 2 guys have to combine, okay? All right, so going back to the original statement, the rate of an elementary step is determined by its molecularity. Unimolecular, bimolecular, Ter-Molecular, etc. The number of molecules that have to collide in order for a reaction to happen. So what is the molecularity of the following reaction? Would be, and all you have to do is look on the reactant side. You're not looking on the product side. You're only looking on the reactant side. Intermediates. Let's get back to those. So here is our proposed mechanism. Remember, this is our guess for proposed mechanisms. It's based on the experimentally determined rate law. These are both elementary steps in our proposed mechanisms. So just to be specific, intermediates don't appear in the overall reaction, but they appear on the product and reactant sides of elementary steps. The product side of an earlier step, the reactant side of a subsequent step. And they are produced in that earlier step and consumed in a subsequent step. So an intermediate is formed and consumed during the reaction sequence. When we determine the overall reaction from a proposed mechanisms, the intermediates get canceled. Reaction mechanisms, a series of steps, of elementary steps that must satisfy 2 criteria, 2 requirements. The first is the sum of the elementary steps must give the overall balanced equation for the reaction. So if you remember from Chem 1, adding up reactions in Hess's law, you cancel things in different reactions that are on opposite sides, and you add the things that are on the same side. Okay, so sum of the elementary steps have to give the overall balanced equation for the reaction. The mechanism has to agree with the experimentally determined rate law. And I would remind you that the rate of an elementary step is dependent on its molecularity. Second criteria is that the mechanism must agree with the experimentally determined rate law. So you started this process by determining the rate law in the laboratory, and now you're looking at a mechanism that you've proposed, and that mechanism not only has to add up those elementary steps to give the overall stoichiometrically balanced equation for the reaction, the mechanism has to agree with the experimentally determined rate law. You have to check your proposed mechanism to determine if both criteria 1 and criteria 2 are met. Okay, so here we go. We're going to do the first criteria. Here is the balanced reaction. Here's your proposed mechanisms. Now, the first thing to do is to cancel the intermediates, and we can do that. Nitrogen trioxide is an intermediate. It's formed in an earlier step, used up in a second step. We can also cancel one of the NO2s because it appears on the reactant side in an earlier step and a product side in a subsequent step. Now we simply add them up. So we've got NO2, just one of them, and carbon monoxide. And now we've got nitric oxide, we add that, and carbon dioxide. And we compare the sum of the elementary steps for our proposed mechanism to the original reaction, and we see that they indeed do match up. Okay, this reaction and this reaction are the same. So we have met criteria number 1, that the sum of the elementary steps is equal to the overall reaction. That's stoichiometrically balanced. Second criteria. The second criteria says in multi-step reactions, we often have one step that is much slower than all of the others. We call this the rate limiting or rate determining step. So you'll probably see it written as RDS, might be rate limiting step, RLS, but RDS is pretty common, just stands for rate determining step. Okay? Now, the rate of the reaction is dependent on the rate determining step. Think about it this way. If I go to the grocery store, and my shopping is really simple, so I know exactly where I'm going in the grocery store, get my stuff, and then I go to the rate determining step, which is mostly the rate determining step in the grocery store, and that is the checkout aisle. There's always somebody who doesn't use credit cards, they use a checkbook, they reconcile their checkbook, and or there's some kind of a problem in the checkout line. So that's usually the rate determining step afterwards. And sometimes I need a really fast step afterwards. Maybe I have to use the restroom, I have to have somebody watch my cart. That's usually pretty quick, but it's usually the checkout line that is the rate determining step. So the rate law is based on the molecularity of the rate determining step. So the experimentally determined rate law has to agree with the molecularity of what you're proposing is the slow step, the RDS, the rate determining step. So here is our proposed mechanism. Okay, we're proposing that the first step is the slow step. Okay, now we know that it's bimolecular in NO2, and we're proposing that the second step is a fast step. And that makes sense with our analysis because carbon monoxide in the experimentally determined rate law is zero order. It has to be there, but it does not affect the rate. So we're proposing that this is a fast step subsequent to the rate determining step, the slow step, and it's bimolecular in NO2. Now, if you remember what the original experimentally determined rate law was, the experimentally determined rate law is equal to K times NO2 second order. And that makes sense for a bimolecular in NO2 first step, slow step, rate determining step. I want to take you back to slide 73 where we said that the rate of an elementary step is determined by its molecularity. So even though for overall mechanisms with multiple steps, you can't write the rate law based on the stoichiometry of the reaction, if what we're talking about is an elementary step and it is the slow step, okay? And remember, the slow step, what we're suggesting is the slow step for this proposed mechanism is this. Okay, so that was our RDS in that mechanism, and it's bimolecular in NO2. Then we did the experimentally determined rate law, and we came up with rate is equal to K times NO2 second order. Now, if this is the slow step and the rate of an elementary step is determined by its molecularity, this would not only be the experimentally determined rate law, it's also the rate law for the slow step. Okay, so the rate of an elementary step is determined by its molecularity. So let's see how to think about this clicker question. Use the rate laws given below to determine which reaction is most likely to occur in a single step. All right, so one of these reactions is a single step reaction. That means one of them is actually an elementary step. And if one of them is an elementary step, then one of these rate laws with that elementary step will be consistent with the molecularity of that single step. Because we know that the rate of an elementary step is determined by its molecularity. So looking at the rate law first, I see that this is unimolecular in NO2 and unimolecular in F2, but bimolecular overall. So I go over here to this proposed single-step reaction. I see, well, this says it's bimolecular in NO2. That I have to have a collision between two NO2 molecules. So this rate law fails based on this comparison. The coefficient is 2. Remember, we're proposing this is a single-step reaction, and the rate law is dependent on the molecularity of that single step. So the coefficients in that case do tell us whether it's bimolecular, unimolecular, ter-molecular, etc. And this rate law says unimolecular in NO2, and the reaction says bimolecular in NO2. That is not a match. So no match. Here we have a reaction that says unimolecular in H2, unimolecular in Br2, but bimolecular overall. So we've got unimolecular in H2, that matches, but we've got 1/2 molecular in Br2. So is that a match? No bueno. But let's take a look at NO. We've got a coefficient of 1 for NO, a coefficient of 1 for O2. We've got an order of 1. So we're unimolecular in NO, we're unimolecular in O2. Our exponent is 1. We're first order in NO, first order NO2. That is definitely a match. Okay? Take a look at the last one. It says that we are unimolecular in NO2 and unimolecular in CO, bimolecular overall. And we see that we're bimolecular or second order in the rate law for NO2. So that is not a match. And there's no carbon monoxide, okay, in our rate law. So if this were the elementary step, then it's reasonable to suppose, if it were only a single step reaction, that carbon monoxide would not be zero order in the reaction. And this is what kills it. This is coefficient of 1, and this is second order. So that is not a match. Okay, I think that's enough of reaction mechanisms.